like to start thanking the organizing committee for inviting me today. And I'm going to try to talk about some of the molecular and polymer we have developed at Northwestern for organic field effect transistors, and a new methodology we have developed to enable low voltage OTFT using very thin insulators. This is the line of my talk. I'm going to start with a very brief introduction. Why we are studying these materials, example of N-type and P-type semiconducting materials, example of dielectrics, and this new methodology, and summary and acknowledgement. Why we are studying this material, the basic idea is very simple. It's trying to fabricate part of electronic components using solution processable methods. These materials, they don't have to be organic molecules. I'm an organic chemist, but if it works with solution processable silicon, that would be fine. But the basic idea is to try to use printing methodology to fabricate some of these circuits. Obviously, we cannot compete with single crystalline silicon. The performance is so much better. It's impossible. But there is some neat application, and there is some performance which this material can compete, such as amorphous silicon or amorphous semiconductors. And the materials which are needed are shown here. You need semiconductors, you need dielectric, and you need the conductors, because these are the components of the TFT. And for those who are not so familiar, this is the OTFT structure. You have it's a three-terminal device. You have your source, drain, and gate conductor, your semiconductor, and your dielectric. You apply a bias between source and drain, but if there is no bias on the gate, this semiconductor has a very low carrier concentration, so there is no current. You apply the bias to the gate. This is the action to create charges at this interface, and you get current out from these devices. And what we are trying to complete in terms of performance are shown here. Mobility on the order of 0.11, as showed the previous speaker, on-operation on these numbers. And these are the goals, what we are studying in Northwestern. The first goals come from looking at these molecules. If you look at the P-type molecules, these are very expensive. There's many molecules which are quite good P-type semiconductors, such as pentosine, excellent P-type semiconductors, but the N-type are much less developed. So there is a need to understand and prepare new N-type material. This is the first goal. The second goal is in terms of dielectrics. We cannot operate these devices on these voltages. About 100 volts are way too far. So you need to develop dielectrics which are compatible with both P and N-type semiconductors if you want to make CMOS. And you must enable low voltage devices. And the third one is these new methodologies to use these very thin insulators. Semiconductors. So we have been studying N-type semiconductors for a while. We have developed a number of molecules, both based on oligothiophene mainly, and replacing some of the thiophene with perfluorine, introducing carbonyl, and using Rylene type structures. I'm going to go through it very fast. Let me start with this slide because it's the way we started. This was about 6 years ago, and what we know from the beautiful work by Garnier and Hotta, that this kind of molecule are very good P-type. And the question was, can we make N-type oligothiophenes? Those were unknown. And what we did, we replaced the periphery of these cores with fluorocarbon chains. Fluorocarbon has a very strong electron withdrawing group, should lower the energy of the HOMO and the LUMO of the molecule. So in principle, you can make N-type materials. This was our feeling, and this is what we got for this kind of molecule. We obtained an N-type conductor with a mobility on the order of 10 to the minus 2. It was pretty low, but it was an initial step. And what we did more recently is to prepare the whole family of fluorocarbon substitute oligothiophenene, and we studied really in detail the effect of the stereochemistry, the regiochemistry, compared to the hydrocarbon and the substituted system. And I don't have time to go into the details. But for this kind of molecule, for an optimized N-type semiconductor, we increase the mobility to 2 orders of magnitude. We are on the order of 0.2 right now as an N-type material. what we did more recently is to change a little bit the chemistry. And what we did is, instead to introduce fluorocarbon at the end of the molecule, we introduced this perfluorine. And there's a reason for doing so. The first reason is an electronic effect. Again, we are replacing an electron-rich thiophene with an electron-poor aromatic union. And this should, again, lower the energetics of the molecule. The second reason is a steric effect. We are replacing a 5-member ring with a 6-member ring. And you know there is a change in the twisting along the pi backbone. And also this should affect the energetics of the molecule. The third reason is the effect of the regiochemistry. Here we move this arene from the end of the molecule into the core, but this molecule remains very, very linear. This is really important to achieve a very good packing. And the fourth effect is the effect of crystal structure. Professor Pu was saying, pentacene likes to pack in this herringbone type motif, which is really important to achieve very high mobility. But if you look at the crystal structure of, for example, benzene or perfluorobenzene in the solid state, they like to pack in this herringbone type motif. But if you prepare a solid solution, 1-to-1, perfluorobenzene and benzene, they like to pack in a cofacial manner. And when you think about cofacial molecules, they like to stay very close to each other. So the idea is, can we change the crystal structure of these molecules? This was a big question. Let me skip this one and go to the answer of the crystal structure. The packing motif of these molecules are completely different than alpha-16. They don't like to pack in a herringbone, but they really like to pack in a cofacial manner. You see formation of these dimeric species at a distance of the order of 3.1 or 3.2 angstrom, which are very, very close. So we achieve this very close packing, and we get N-type mobility of the order of 0.4, 0.5. So these are another interesting class of molecules to get that. These are more recent results, and here we have introduced carbonyl between the thiophene and the perfluoro chain. And there is some reasoning again here. This is a very strong electron withdrawing group, but not only by sigma, but by pi action, so by resonance structure. And this should stabilize the formation of the radical cation, the anion, if you think about the Marcus type like charge halving motif. In addition, you can functionalize this carbonyl here in a different way, so you can use different groups, and I'm going to show you an example. And in addition, you can put this carbonyl into the core between the thiophene, as shown in this molecule. And with this family, I don't have time to go into the detail, but we got very good N-type conductor. You can see here the energetics in terms of reduction potential. For the unsubstituted system, for the alkyl system, the reduction potential is of the order of 1.9. When you put only fluorocarbon, you have a reduction of the order of 0.4 volts. But when you start introducing carbonyl groups, the effect of the reduction potential is much more strong. We have variation of the order of 1.5 volt in the reduction potential. And this one is an N-type conductor. This is an example of this molecule. And we got a mobility on HMDS, silicon dioxide treated substrate of the order of 0.6. Instead of polystyrene treated silicon dioxide, we got a mobility of the order of factor 2. So again, an important properties of the dielectric to affect the mobility of the semiconductor. This is a very nice example, and we are studying why this is happening. And this is one of our last oligothiophene family we have developed. And here we put everything we know together in the same molecule. We kept the thiophene because we like it. We kept the carbonyl because it has a very good effect in lowering the energy of the molecule. And we replaced these perfluoroalkyl groups with perfluorarine. And this is very important because in this kind of motif is a pi conjugated, so you can make pi conductive polymers. And this is an example of polymer we have made. Also, all the data I've shown you so far are on vapor deposited molecules, but ultimately you want to make solution processable devices. And the idea to use this carbonyl and this perfluorine motif is, if you look at the crystal structure of benzophenol, very simple diaryl ketone. It's not flat. You have a twist into the core. This twist on the order of 30, 35 degrees. And what our hope is, if we have a twist about this angle, we might make molecules which are more soluble. And also the effect of the crystallinity is important. We know from the previous study that this perfluorine really helps to pack the molecule in a very good manner. So these are examples of this crystal structure of some of these molecules. You can clearly see the effect of the packing, the effect of the twist. There is a twist in this angle of the order of 35, 40 degrees. The molecules are very, the films are very crystalline. You can see all of this Bragg reflection for the vapor deposited, but also for the solution deposited films. And in terms of mobility, we got an N-type mobility, which is on the order of 0.5 for the vapor deposit field, but also on the order of 0.2, 0.3 for a solution cask N-type molecule. And also, it's really important when we think about printing and we print some of these molecules is rheological properties, viscosity, adhesion, cohesion, how this inks goes into your substrate. So it's really difficult to control these properties just playing with the property of small molecules. But if you can mix the small molecule with the polymer in a proper manner, and it's something we can do, we can control the viscosity of the solution and achieve very good crystalline films from this mixture of components and get mobility on the order of 10 to the minus 2 as printed devices. And these are an example of flexicographically printed semiconductor. This is a work done at Polymeric Corporation. This is the last class of molecule we developed in terms of N-type semiconductor. These are these Rylene structures. These kind of core are obviously known. These have been studied quite well at IBM. They got quite good N-type mobility. The problem, the very high threshold voltage, and they are not air stable. So what we do, we introduce this cyano group into the core. And this really helps to lower the energy of the molecule. And we get a reduction potential close to zero or even positive for some of these molecules. So these are very strongly electron depleting molecules. And these are N-type semiconductor, very high N-type mobility in air, very, very, very stable molecules. And these are really give us good result in terms of enabling CMOS technology. So we can print this N-type with a well-known P-type. And we made, for example, 5-stage ring oscillation. All everything is from printing. The frequency is on this order for vacuum and air devices. And we can make this D flip-flop kind of logic. So now let me switch from N-type. We have been also working on P-type. And one of the reasons we started working on this P-type is we were trying to make bottom contact devices. And when you think about bottom contact devices, bottom contact, bottom gate, or bottom contact, top gate devices, in either kind of configuration, you have to worry about two important things. The first one is how is the contact? How is the interface between your conductor and your semiconductor? This is really critical. The other important thing is, if you think about a top gate structure, such as shown here, you have to print your dielectric on top of the semiconductor. And people try to solve this problem by using orthogonal solvents. You know, you use a solvent to deposit the dielectric, which doesn't dissolve the semiconductor. But this works, you know, in academia, like me. You can use, for example, ethanol, and you can use chlorobenzene for the semiconductor and ethanol for your dielectric. But in practice, you cannot print using chlorobenzene or this kind of solvent. You have to use ethanol, ethyl acetate, this kind of solvent. So it's really important to get the right. It's really difficult to find orthogonal solvent which work for real application. So ideally, you want to have a semiconductor which is completely insoluble after you print. And what we did, we used a non-P-type polymer, this fluorine derivative, and we mix it with a semiconducting crosslinker. So semiconducting polymer plus semiconducting crosslinker, we spin coat it, this material becomes completely insoluble. It doesn't get attached anymore. And we observe a couple of advantages. First of all, we solve the problem of the contact between the conductor and the semiconductor. These are examples of TFP devices only. You can see the top contact and the bottom contact behave very differently. And the bottom contact behave very erratic, depending on how the semiconductor is deposited on the conductor. It really behaves not reproducible. Instead, with our semiconductor polymer blend, we always see very good reproducibility between top and bottom contact devices and comparable properties. And also we can make top gate structure quite easily. We can print the dielectric using ethanol, THF, or xylene, which are completely different solvents, but all of these solvents, they don't attack the semiconductor. So let me switch to dielectric. And why did we start studying the dielectric? And the answer is looking at these voltages, which are very, very high, and why people are using, and also ourselves are using such a high voltages. The problem is the mobility of the organic is quite low. So in order to achieve enough current, you have to increase the gate and the drain voltage to get enough current out. An alternative approach could be to increase the capacitance only of the gate change. And you can increase the gate capacitance by increasing the dielectric constant or decreasing the thickness. It's quite easy, or relatively easy to increase the dielectric constant. But control have a very good insulator when it's very, very thin, that is quite difficult as a challenge. So we have developed two methods. The first one is to using a multiple dipping technique. So it's called self-assembly multi-layer structure, in which we thought about two components. One component we call a pipe component, which should increase the dielectric constant of the insulator, shown here. And the second component, which should pack very well and provide a very low leakage through the gate. And these are the two building blocks to make this insulator. This is a steel basolium salt. It has a lot of pi electrons, so they move very, very fast, high dielectric constant. And this hydrocarbon chain, which likes to pack quite well, very, very closely, should decrease the leakage curve. And of course, we link these building blocks using siloxane chemistry, which forms sigma bonds extremely strong, like silver. And I don't have time to go into the detail, but we can prepare this multi-layer structure. We start from any surface which has OH groups at the bottom, and if you do it just at the right condition, with the right solvent, the right concentration, we can react only one of these two heads to the surface. And then we cap this part with this chloro reagent, which forms a planarized surface. And at this point, this surface, after hydrolysis, is the same as this surface. So we can do the same chemistry on top of here and go on and on. We can prepare multi-layer structure. And we made different kind of very thin insulator from about 2.3 nanometer up to about 5.5 nanometer. We can make it bigger, but these are the thinner we can make using only these two components. And we compare the properties of this non-insulatum using only the alkyl component, only the bi-polarizable component, and using both of them. This is the combined structure I was talking about. And we made offense, obviously. First of all, we check the quality of the insulator. And there's two ways you can check the quality. One is by using electrochemistry. So if you put a piece of ITO into a solution which has ferrocene, and you check the electrochemistry, you see the redox properties of ferrocene. If we passivate the ITO surface with our insulator, you shut down completely the electrochemistry. So this is a film which has been fault-free. This is one important information. The second one, using quantitative leakage current in the MIS structure. This is the leakage current for the bare silicon substrate with the native oxide. And when we put our insulator, you can see the drop in the leakage current between 7 and 9 orders of magnitude. So very good insulator. The capacitance of this kind of insulator is quite high. Obviously, they are very, very thin. capacitance changes depending on the structure. I don't have time to go into the detail, but the capacitance ranges between 400 to 700 nanofarad centimeter square. And more importantly, what is important to check is the offense properties. This is a control device. If you use silicon dioxide, 300 nanometer, this is the operating voltages. And this one, if we use out one of our dielectric, you can see the reduction in the operating voltages, few volts. And also, this dielectric is compatible with the N-type. This is sometimes trivial for dielectrics. Sometimes they work well for P-type, but they don't work well for N-type material. And we also made some flexible and on ITO, which are different kind of experiments. This is another interesting issue. We were talking to John Rogers at the University of Illinois, Urbana-Champaign, and he has a technique where he can print carbon nanotube on silicon dioxide. And these are the transistor performance for carbon nanotube printed on silicon dioxide. The operating voltages are reasonably high, depending on the thickness of the silicon dioxide. But you can clearly see the hysteresis, this charge trapping at the interface, which is extremely high. So we use our nano-insulator. In this case, the insulator was about 15 nanometer. You can clearly see the reduction. There is no hysteresis. The voltages are very, very low. The mobility is on the order of 30, 40. This is another example of application. Here we use zinc oxide nanowire. And again, very low voltage. The mobility for this zinc oxide nanowire is actually very, very high. We don't fully understand right now why the mobility is so high. We made many devices, there are many batches. We really reproducibly see this number. So it's something we are investigating more in detail. But this is a result of a few days ago. And one of the interesting applications could be in the space application of some of these materials, especially for the nanowires. And we studied this kind of transistor comparing with silicon dioxide. John was already doing an experiment with silicon dioxide, and he was seeing these huge changes in the threshold voltages when it was proton irradiated at 5 or 285 kilo amp. These are proton irradiation. If we use our nano-insulator, we don't see any threshold voltage here. This is really important. Again, we don't know why this is happening. We don't have an explanation at this time. This is what we observe. And the second class of material are these, for dielectric, are these polymer blends. And we are interested in working on this self-assembled multi-layer structure, but this is more a multiple dipping technique, where you can prepare your dielectric layer after layer. The problem is very difficult to translate it into a printing process. It's something that is not easy. Ideally, people want to use polymer. And what we did here, we use the same approach we use for the semiconductor. Here we use an insulating polymer, such as shown here, and an insulating cross-link. You mix them together. If you do it right, you can spin coat this insulator, and they are very good quality. We can spin coat these fields. I don't have time to go into the detail, but just believe me, we can make very thin insulator on the order of 20 nanometers, and they have very low leakage current, about 24 megavolt per centimeter. The capacitance obviously can be very, very high, or it can be low, depending on the thickness of this material, so we can control the capacitance depending on that. And obviously we could make offense with different kind of material. Again, with these polymers, dielectric, we can get very low voltage operation. We never try to optimize the mobility of this device, and we grow pentacene here at room temperature. We never tried to optimize the mobility of the pentacene. It was just our goal to see if we could make these kind of devices using this kind of dielectric. And this is an example of stability of pentacene devices. Here we can turn on and off the pentacene a number of times. Right now we are about 200 hours actually turning on and off. And the characteristics don't change. The threshold voltage doesn't change. This is also an important parameter. It tells you the quality of this interface between the dielectric and semiconductor has to be quite robust. And we can print some of these insulators. This is an example of gravure printed insulator. This is a bed sample. this is using the same formulation we use for spin coating, for printing, and the results are actually not good. But if you do just right, we can get quite good printed insulator with very good quality, very smooth surface. So it's extremely important not only to have a composition, but also to optimize it for the process we want to use. And these are examples of offsets we made. Unfortunately, I cannot disclose the result at this point. The last 2 minutes, do I have 2 minutes? 4 minutes? Okay, the last 3 minutes, I'm going to show you an example of device fabrication. And this came out because we were looking at the literature, and every time you see a very thin insulator, like between, like our case, 5 nanometers to 20, 25, 30 nanometers, every time you see a common gate structure. This is a huge piece of silicon wafer or a piece of aluminum, and this we spin coat or we deposit up layer by layer our insulator. But this is a common gate structure. This is not useful for devices application. What you would like to do is instead you have your gate lines separate and your source and drain line, and you can connect them, but you cannot use a common gate structure. This is completely useless. So we need to make something like this. The problem is if you want to spin coat or print a very thin insulator on top of pattern gate line, your device yield is extremely low. You always have defect. If you spin coat, you have shadow effect due to the spinning. You never get anything working. But if you really want to use this nano-insulator on this structure, so what you need to have instead is a structure which looks like this, where your gate line are inside your substrate, and you have a planarized surface. And obviously you want to have a planarized surface which is flexible and which is a polymer. And the way we did this one is the following. We took a piece of silicon or glass substrate, we printed or we deposited metal, our gate lines, and then we hot press using polymeric foil or powder, a polymer, just right at the right temperature. And so you end up with a structure like this. And if you peel off this structure at just at the right temperature, you get a new substrate, which is your polymer basically, in which your gate line are embedded into it. So there is a self-planarized embedded gate line. And on this surface, you can spin coat or you can deposit your dielectric, your semiconductor, and you can print or deposit your source and drain line. And these are examples of embedded line. For example, this is aluminum with different length, gold, we did it with a silver epoxy printed line. And here the polymer is usually PMMA. And this is the question was, are we really getting a flat surface? Is the surface really planarized? And this is some AFM of the side wall. This is an example of aluminum before planarization. And this one after planarization and peeling off your PMMA. You can see the interface between the PMMA and aluminum. And this interface is completely planarized. And on this surface, you can spin coat your dielectric. And we did it also for gold, or we did it for printing it. I mean, if you print a line, very, very rarely you can print lines which are less than 2 or 3 micron. And here we printed about 70 micron lines, so very, very, very thick line. And of course, these are very rough lines. And after planarization and peeling off the substrate, we get silver printed epoxy line with a roughness of the order of 8 nanometers, so very smooth surface. And we can deposit our very thin insulator about 20 nanometer. We measure the leakage. It's controllable. This is the capacitance. Of course, it's quite high. These are initial results. But importantly, we can make these offsets using pentacene. This is a planar gate pattern line using pentacene. We're using an N-type, such as caprolactylocyanine. Or in this case, we use gold with pentacene. We use gold, or we use silver epoxy. So different kind of compounds. So in conclusion, I show you some example of N-type materials we've been studying actually for a number of years. Example of application in CMOS printed technology. An example of P-type semiconductors using our cross-linking chemistry. I show a couple of examples of dielectric and a new method to prepare very low voltage self-polarized OPEX structure. And I'd like to conclude thanking Professor Marx for giving me a lab to work with, Mark Ratner and Wasilewski for the computation and the work on writing structure, all these people. And I would like to thank Yoon Han Yang, because he's actually the one with me who really did most of the work in the lab. He's an exceptional guy. And unfortunately, he's leaving to Harvard, so I'm going to be alone soon. And thank you for your attention.